Okay, so in this video, the next one dealing with calculations, we're going to calculate equilibrium concentrations using Kc and given initial concentrations. So in this case, we're going to have to use the given value of Kc and determined values of equilibrium concentrations. And so we're going to plug and play, and that will allow us to calculate the equilibrium concentrations of constituents in a reaction. So why don't we get started on that? So here's our initial reaction. So if you notice, it's pretty straightforward. It's all 1-to-1 ratio, so that simplifies things a little bit. But let's look at what we're given. So we're given this reaction, balanced as written, and we have a Kc value of 4.06 at 500 degrees C. You don't have to worry about the temperature. And you have 1 mole of carbon monoxide, sorry, 0.1 mole of water placed in a 1 liter reaction vessel. So moles and volume have to convert to concentration, moles per liter. That's an easy one. So the question is, what are the equilibrium concentrations of the reactants and products at equilibrium? So we're determining equilibrium concentration. So the first step here is going to be an ice table. And so there's our reaction. And what I certainly suggest you do is put your ice table directly below an equation. If that means rewriting an equation, I would recommend doing so. It doesn't take that long, and then you can get everything right in front of you in preparation for a substitution. So concentrations, initial concentration of carbon monoxide and water, 0.1 mole per 1 liter, so it's 0.100 molar for both. Initial concentration of the product, CO2 and water, 0 for both, as is often the case. Now here, we have to do something a little different. We are not given any equilibrium concentrations. In fact, the question is, what are the equilibrium concentrations? So that's what we're trying to determine. So we don't know what these are, and we don't have any change information. So this is where we have to introduce a variable. And I would say the most common variable is x. So we're going to say, let the change in carbon monoxide equal x. And because it's a reactant, it's negative x. So similarly for water, the change is going to be negative x. 1-to-1 ratio. The change in carbon dioxide and hydrogen is going to be x for both, and it's going to be plus x, because those are products and they're going to increase. So this is where it's 1-to-1 ratios throughout our equation. So the stoichiometry makes those change determinations quite simple. X is the variable, and it's all 1-to-1, so all single x's. But now we can calculate the equilibrium concentrations. So 0.0100 minus x, 0.100 minus x for water and carbon monoxide, x and x for hydrogen. So now we actually have our equilibrium concentrations, and these aren't numbers, they contain variables. So that's going to change how we solve our problem a little bit. But solve it nonetheless, we can. It's actually not that difficult. So there's our equilibrium concentrations, and we're going to plug it into our equilibrium expression. Let's just get that up there a little bit. And so let's get going. So we were told actually that the value of Kc is 4.06. So equilibrium expression, substitution, 4.06 equals equilibrium concentrations. CO2 and H2 are both x's, so it's x times x. And carbon monoxide is 0.100 minus x and 0.100 minus x. So there's our concentrations. Now again, this might look like a fairly complex thing to solve, and it would be. You're going to generate a quadratic equation, you have to use a quadratic formula. But if you have a quick look first, and I always recommend this, what if we took the square root of everything? Well, square root of 4.06, we can determine that it's actually 2.01 equals, what's the square root of x squared? Well, it's x. What's the square root of 0.100 minus x times 0.100 minus x? Well, it's 0.100 minus x. So we've greatly simplified that problem. This, as you probably are aware, is known as a perfect square. Whoops, need an R in there. So when you have a perfect square, take the square root. You can always get the square root of a number, and that greatly simplifies the problem solving for the rest of the problem, because now it's just a simple case of isolating x, and when we do that we get, so you're going to solve for x here. I'm not going to go through that because that's pretty simple algebra. You learned that fairly early in your math career. When we actually calculate a value for x, we get x equals 0.067. Okay, but x is not the answer. The question is, what are the equilibrium concentrations? So based on our variables, concentration of CO2 equals the concentration of hydrogen gas, which we had allowed as being represented by x, so it's just x, so 0.067 moles per liter. Concentrations of carbon monoxide and water are going to be the same, but they're based on 0.100 minus x, which is 0.067, and that equals 0.33 moles per liter. So don't forget, answer the question. The question was, what are the equilibrium concentrations? And so don't leave it as x. X is not the answer to the question. Alright, so we just let our change component of our ice table equal a variable, or be represented by a variable, and we do everything else the same, and so it just comes into plugging in equilibrium concentrations. And as I said in this video, the emphasis is on look for that perfect square, because if you get a perfect square, life is wonderful. So let's try another one quickly. So we'll go through this one. It's pretty much the same. There's our reaction. Don't forget to balance it. And here again, we're given given a value of Kc, and we're given initial concentrations. And so we're asked to calculate all equilibrium concentrations. And so once again, the value or the ice table comes first. So initial concentration of hydrogen is 0.2 moles per liter. Iodine is 0.2 moles per liter, and 0. We're going to let our variables be x. And so this is where it's a little different. X for hydrogen change, x for iodine change, it's going to be plus 2x for hydrogen iodide change because of the stoichiometry. For every 1 molecule of iodine used, 2 molecules of hydrogen iodide would be produced. So the change is twice that. So now we have 0.200 minus x, 0.200 minus x, and 2x for our equilibrium concentration of iodine. So once again, we're going to plug this into our equilibrium expression. There's our equilibrium expression, and so Kc was 64.0, Hi is 2x squared times 0.0200 minus x, 0.200 minus x. So there's our equilibrium concentrations into our equilibrium expression. Well, once again, we have a perfect square. Take the square root of both sides. So again, we look for that perfect square. We have it. 8.0 equals 2x divided by 0.200 minus x. And we solve for x again. And when we solve for x in this case, we come up with x equaling 0.160. And again, concentrations, hydrogen and iodine are the same because the initial concentrations are the same and they change by the same amount, but that is 0.200 minus x, and so that equals 0.0400 moles per liter. And finally, the concentration of hydrogen iodide is equal to 2x, and so that equals 0.320 moles per liter. And so there is how you find equilibrium concentrations given k and given initial concentrations, and solving for x, solving for those variables that now appear in the change line of your ICE table. And so the first step in this process is look for the simple root out, look for that perfect square. If you get the perfect square, it's quite simple to solve. You can also solve using the quadratic formula. That is, as we will see, a little more difficult. You have to be very careful when you solve that way. But that concludes this video.